Yes, so we will have the overview, like introduction from the hands-on leaders. But while they are doing this, I want everybody who's scheduled to giving a poster pop today to come, like please line up here so that we can, right after the 15 minutes talk, we can have the poster pop going on. So if you don't know your schedule, you can find it on the Sagan Workshop website on the agenda page. There's a schedule there. You can find out if you are scheduled for today. Thank you. Sebastiaan.
Okay. Okay. Hi, everyone. So I'm Sebastiaan Haffert from Leiden Observatory. I'm going to lead the hands-on session for optical modeling. I'm doing this on behalf of Emil Poor, who couldn't be here. So we're going to do optical modeling of chronograph systems. For that, we're going to use HCIPy, the high contrast imaging package for Python. It's open source software developed by Emil Poor. You can see the websites there. And it's a software package for full end-to-end modeling of chronographic systems, where you can do model adaptive optics, wavefront sensing, coronography, photonics, there's intrinsic support for polarization, which is pretty unique. You can do general physics, optical propagation, physical optical propagation, and we're currently developing automatic differentiation through JAX. So that means it's very flexible. And this is all done in Python. And it's also multi-platform. So that means you can use it on Windows, Mac, or Linux, doesn't matter. It should work on all of them. Okay, so what are we going to do today? You're going to learn how to make a PSF in the beginning, so you'll get familiar with HCIPy. So here I'm showing a couple examples, clear aperture, GMT. Second step is we'll learn how to model chronographs and how you can make the curves that David and Eva showed today. And we'll focus a little bit on aberrations, like how do aberrations impact the chronograph. And after we've done that, we have actually done 3 blocks, which sort of concludes the hands-on session. And then there are 2 group projects. One is about adaptive optics, so that's coronography and high contrast imaging for ground-based telescopes. And then we'll try to see if we can make videos where you actually do atmosphere propagation through a chronograph. And the other option is to do electric field conjugation, which is a way to handle aberrations. So here you can see an image with an aberrated chronograph, and then in the white area, you try to remove them by using a deformable mirror to do active control. So those are 2 of the group projects that we will try out. And that ends the hands-on session for optical modeling. You can leave it on.
The next one is a movie because Jason is not here yet. So,
hi everyone, my name is Jason Wang. I'm an assistant professor at Northwestern University in CIERA. I'm probably on a plane right now or just landed at the airport at LAX, but I will be leading hands-on session 2 on PSF subtraction, and we'll be using this package called PyClip that I'm the lead developer of. As part of hands-on session 2, you'll be working with real data, so we'll be looking at using real Keck data on the star HR 8799. It is known to have 4 directly imaged exoplanets. You might have seen this movie of these 4 planets in orbital motion. We'll be actually reducing data from this movie. We'll be able to make some of the individual frames from this movie. So you'll make your own detections of these 4 planets from the Keck data. In doing so, you'll learn how to make compute detection metrics from our data, such as making detection maps to see the point sources in our data to detect these 4 planets. You also learn how to make contrast curves, which assesses the sensitivity in our images as a function of separation. Ignore these bumps. This is due to the fact that we have real planets in our data, not non-detections. You'll learn how to measure planet properties. So if you have one of these planets that you have detected, how to measure their position with respect to the star, and how to measure their brightness with respect to the star. And If you want to learn further, there for the you can also take the. We also have some potential project ideas. You can tweak the data reduction parameters in the data to try to improve the sensitivity of the detections. You can measure all of the planet's fluxes, convert them into luminosities, and convert those into masses to basically go from a brightness in your image and be able to infer a mass of these planets. And lastly, we have given you 2 epochs of Keck data, so you can measure the positions of the planets in each of the 2 epochs and use the open source package Orbitize to measure the orbits of all of these planets. So great. Hope to see you all soon.
Up here, this is forward, back, and the pointer.
Hi, I'm Ron. Can you hear me? Okay. Hi, I'm Rhonda Morgan. I will be guiding you through the hands-on session on yield modeling. In yield modeling, we're seeking to answer a few basic questions. The main one, which is how much science will our mission do? And 2 other important aspects of that. How do the engineering design choices impact our science return? And how can we optimize our mission operations in order to improve or support our science returns? So we'll learn about the basics of yield modeling for direct imaging of exoplanets for space missions. The scope of what we're going to cover will include how to compute completeness, and by this we mean really probability of detecting a planet around a single star, and how our astrophysical assumptions impact completeness and the rest of yield. How do we compute integration times? How do we do all the radiometry on that? And then we also have to account for mission constraints. Usually there's a solar avoidance. The telescope can't look too close into the sun or else it'll fry itself. But then also we have anti-sun constraints usually, such as where solar panels or thermal radiators might be placed. And lastly, we're going to put it all together and say, how do you put this into a full end-to-end simulation? So how can you plan? But this will be in the group projects. If you're interested, how do you put in a full end-to-end simulation? I wanted to say one more point about the group projects. There are 2 options for group projects. One, you can focus on how do you optimize exposure time and completeness, and the other one is how do you do an end-to-end scheduling of a mission. I hope you're looking forward to it.